Okay, in this next series of videos, we're going to be tackling non-inertial reference systems. Remember, for a frame to be inertial, it has to be moving at constant velocity, which could include being at rest. Now we're going to extend it to the possibility of frames that don't satisfy that. So that leads to a natural question. Since Newton's laws only apply in inertial frames, why would we want to do physics in non-inertial frames? And there's two ways, at least, that you could go about answering that. The first is a really trite answer. We live in a non-inertial frame. The Earth is orbiting the Sun, it's spinning on its axis, the Sun is orbiting about this supermassive black hole in the center of the Milky Way galaxy, yada da yada da yada da. But most importantly, the Earth is rotating on its axis, and since we live on the surface of the Earth, it would be convenient if we could pretend that the Earth's surface was inertial, even if it isn't, because of convenience. Okay, that's cool for the practicality, but philosophically, if you think about it, it seems like it's really a cheat to say that only inertial observers can do physics. I mean, why should they be special, right? And so if we can develop a more extended treatment, then we can put all observers on equal footing. A logical conclusion of this train of thought, by the way, is Einstein's theory of general relativity. All observers treat themselves as inertial in that model, and they just say that they're following their particular geodesic in space-time. So, to that end, let's at least work on extending Newton's second law to an accelerated coordinate system. So, we'll let this black coordinate system, I'm sorry, I want that to be x. We'll let this black coordinate system x, y, z. This one's going to be inertial. And then I'll draw in red another coordinate system. We'll call that one x prime, y prime, z prime. And we'll say that this system is accelerated. Just so we can tie the two thoughts together. Now the position at any moment, the position of the origin of the accelerated frame with respect to the inertial frame will give by capital R naught. So now, if say we're observing some event right here, the two different observers are going to measure two different positions for it. The inertial observer is going to measure R, and the accelerated observer here is going to measure R prime, like so. Okay. So with that, we will say that the inertial position, the position measured in the inertial frame, that would be equal to this plus that, right? Vector addition. So R naught plus R prime. And we can go ahead and happily differentiate this away. So the velocity measured in the inertial frame would be v naught, so that would be the velocity of the origin of the accelerated frame with respect to the inertial frame, plus v prime. So that's the velocity of the object as measured by the accelerated observer. And similarly, we can go ahead, differentiate one more time. And we'll get that the acceleration in the inertial frame would be equal to the acceleration of the accelerated frame, so the acceleration of the origin here, plus the acceleration of the object that the accelerated observer measures. Okay, so since we know Newton's second law in an inertial frame, this gives us a clue for how to bootstrap it. So Newton's second law says F equals ma, so we can go ahead and substitute that in. That'll be equal to m a naught plus m a prime, like so. Now, for an observer in the accelerated frame, what they're going to be measuring is a prime, so that's ma prime. So we'll have to subtract this ma naught from both sides. So f minus m a naught equals our ma prime. So now what do we make of this? So we have a little bit of a sidebar here. This is one of the things that no one ever really explicitly writes down in a physics text, near as I can tell, but most equations in physics can be read as cause equals effect. Now the problem is that the rules of math allow you to add or subtract terms to each side. So one of the tricky things that physicists often have to deal with is figuring out whether something is a cause or an effect. For instance, the whole dark matter thing. Dark matter is one particular model for understanding the structure of a galaxy, where a cause has been posited. Now you could just as easily subtract that term from both sides and stick it over onto the effect side, and you run into various theories that seek to modify gravity. And say that gravity works a little differently than you thought it did. There's a lot of work being done on that. You can eventually tease out which side of the equal sign something belongs on physically, but it's a lot of work. Anyway, enough of that sidebar for the moment. So what some observer would just say is, hey, I know a force because it causes an acceleration. So you would say that some force F prime, some net force F prime, would equal m a prime. So he would say that in addition to all the forces the inertial observer saw, we would have to include this minus ma naught term in as well. So a term like this ma naught usually gets called an inertial term. Other phrases are inertial force or fictitious force. So the problem with calling it a fictitious force, and you do see that a lot, especially in 100 and 200 level texts, but there's sort of a problem to it, because if you ask, is the inertial term real, in quotes, if you're an observer in the primed frame, yes it is. There's really no way that they could do an experiment to show that it wasn't. An example I could think of is just to say, is there any, imagine that you were in some basement room with no windows. Is there an experiment that you could devise that would be able to prove that instead of gravity pulling down on you, it weren't just the fact that you were in a rocket that was constantly accelerating upward? Now let's just take that idea a little further. Let's look, for instance, at a swing hit, just a pendulum bob hanging in our rocket. So at the moment, we'll just have it not swing. So there's our pendulum bob, mass m. And the thing is accelerating upward with the rocket at our a naught. Well, we can go ahead and draw a free body diagram for it. If we were in the unprimed frame, we would draw a free body diagram that showed a force of tension acting up. And we would say, by Newton's second law, that that tension was equal to ma, which equals ma naught. Okay. Now, let's think about how a primed observer would think about this. So our accelerated observer would draw a different free body diagram. As far as they know, they're standing still. So they would say that the total acceleration of the object was 0. They're certainly going to agree that there's a force of tension up, but they will go ahead and add in that force minus ma naught pulling down. They might even think it's gravity or something. So anyway, they would write T minus ma naught equals ma prime, but they would assert that, in their frame anyway, that pendulum bob is at rest. And it's not accelerating. So they would agree on the tension in the string. They would agree that is equal to ma naught, just as the primed observer would. So they would conclude, they would say this sort of looks kind of like gravity. Just with some sort of g prime that was equal to minus a naught. But you say, maybe we didn't take that far enough. After all, pendulous swing, maybe there's some difference there. All right. Again, let's just, because life is too short to mess with elliptic integrals, let's just displace this through a small angle, theta. All right. So there's our mass like so. So again, our unprimed observer would say this thing is accelerating upward at a naught. They would go ahead and draw a free body diagram for the bob, and they would just have the tension there, like so. And they could break it into an x and a y component, like so. So this would be minus t sine theta, that'd be t cos theta, like so. So they would write the equations of motion. For the y component, they would say t cosine theta equals ma naught. So they would get, since the angle is small, that the tension is approximately ma naught, because we would say, since the angle is small, the cosine is approximately 1. Okay. Then looking at the x component, they would say, all right, minus t sine theta would equal our ma, which we can write as ml theta double dot. All right, since the angle is small, we can say the sine of theta is approximately theta itself. And we worked out that the tension was ma naught, so we would write minus ma naught theta is equal to ml theta double dot. Cancel, cancel. And we get theta double dot equals minus A naught over L times theta, and we would identify that as our omega naught, as our omega squared. So we would conclude that omega equals root A naught over L. Okay, so that's how you did it in the unprimed frame. Now let's repeat this exercise in the primed frame. So in the primed frame, the observer in the primed frame would say that there isn't any net upward acceleration. So they would draw the free body diagram by saying that there's again a tension up and to the left, but now that there's a force minus ma naught, an inertial force minus ma naught pulling down. So they would go ahead and write the y equation of motion. They would say t cosine theta minus ma naught equals 0. They would again say, well, since the angles are small, that's approximately 1. They would conclude that t equals ma naught. The x equation is the same, so they would eventually come to exactly the same conclusion, that omega is equal to root A naught over L, whichever way you want to slice it. So the observer in the primed frame, in our closed room that's in a rocket accelerating upward, assuming the rocket is a nice smooth ride, would be completely incapable of distinguishing between that rocket ride and being in a gravitational field. Okay, in the next video, we're going to go ahead and take a look at what happens when our coordinate systems are rotating.